All right, well, good afternoon, everyone. Welcome both to our in-person crew, and then I think we have 70 or so virtually. So welcome to everybody. This is the latest iteration of our Innovation Lab speaker series. This is the third this year. We enjoyed hearing from Bob Wachter from UCSF earlier this year and Roy Rosen from Penn this summer. So we have two more speakers left this year. Today we're excited to welcome Michael Howell from Google, and then later on this month, Ani Ofadile from MD Anderson will be visiting us. So just by way of introduction to our guests today, Michael, I've actually had the pleasure of knowing since we were both college students at Rice University in Houston. I told him earlier today, I believe that was in 1822. So a lot has happened since then. He is currently the Chief Clinical Officer at Google, and he leads a team of clinical experts, doctors and nurses, who provide guidance for Google's health-related products, research, and services. His career has been devoted to improving the quality, safety, and science of how care is delivered and helping people get the best information across their health journey. He's been at Google for 5 years. Prior to that, he was at the University of Chicago, where he was the chief quality officer for that health system. And then prior to that, he was at Harvard Medical School and Beth Israel Deaconess Medical Center. He's practiced critical care medicine for many years, and he's published more than 100 research articles, editorials, and book chapters. And he's the author of Understanding Healthcare Delivery Science, which is one of the foundational textbooks in the field. He's been an advisor for the CDC, CMS, and the National Academy of Medicine. And he's a fellow of the Aspen Institute's Health Innovators Fellowship and a member of Aspen Global Health Leadership Network. So I appreciate everybody's attention to him. We welcome him to St. Louis and look forward to it.
Thanks, Tom. It's interesting. So we rescheduled this a couple of times because of COVID. And so I want to start off with just saying thanks for taking care of sick people over the past couple of years. And for those of you who don't directly take care of sick people, thanks for making stuff that let them take care of sick people and for taking care of them. But I am glad to get to show up in person. And this talk has always, never given exactly this talk before, but it's a little risky to give in a mixed audience because there's sometimes people who've never really heard of machine learning and people who want to talk about like what the optimal batch size is or learning rate in some LSTM. And so if you're here for the latter, like I'm not your person for that. But what I wanted to do was to take a minute and talk about things that I've learned in the past 5 years that I didn't know when I was sitting in the University of Chicago, and I thought I knew a lot about machine learning then. And I put up this chronology because I often feel like I'm the weirdest hire at Google. So the easiest way to think about my background is between 1995 and 2017, I was either training or taking care of sick people and running parts of health systems. And then in 2017, I literally moved to Google for my first industry job ever. And I'll try and tell you what I've learned after being at the epicenter of machine learning over the past 5 years. I'm employed by Google. So my most important disclosure is I'm employed by Google. You share everything that I say sort of through that lens. I get some royalties from books. I've had some funding and I've served on these committees, and I'm supposed to say my opinion's not theirs for them. 3 things for learning objectives. One is walk out understanding the key insight of machine learning and how it's different than some of the things that came before. 2 is have an intuition for what the thing actually learns, which took me a long time to wrap my head around. And then I'll give some really concrete examples of the way that we use machine learning in our research and practice for them. But I guess that we have some shared beliefs, and I have learned over time it's better to just articulate what the beliefs are, and make sure that they're shared. And so the first is that healthcare delivery is really, really complex. And I don't mean complex as a throwaway term. I mean it as a fundamental aspect of providing care. And that means that providing and receiving care is really, really hard. And you see this in statistics. If you run a health system, you know that before COVID, 30% of US hospitals had a negative annual operating margin. You know that you undoubtedly have, I didn't actually ask anyone this, but I suspect you have areas of the health system that are too full and others that are simultaneously too empty. You have to report more than 500 different variations of quality and safety measures that determine a meaningful fraction of revenue. And you have this uncertain future in this particular way of, it's very clear that things are moving to value-based care, but the pace is uncertain. And if you go too fast, you're in trouble. And if you go too slow, you're in trouble. And so the system is truly complex. And that complexity often leads to our intent not translating to our results. What do I mean by that? Anyone who's ever gotten care or helped a family member get care knows that it is cold, impersonal, uncertain, fragmented, and filled with waiting. Any medical students here? So when there's a medical student in the audience, I always ask them, have you ever, before you came to medical school, had you ever seen a fax machine? And the answer is always no. And then now do you believe it's a life-saving piece of medical technology without which the health system would collapse? And everyone always says yes. Just before the pandemic, when it was studied, 70% of physician-to-physician communication that was nonverbal was via fax. So the lived experience of getting care is hard, and the lived experience of providing care is hard. That lived experience comes out in the statistics. Whether it's the health affairs study that showed that 8 million people a year globally die because of lack of access to care for things that we already know work, whether it's this middle of the road estimate of 100,000 people a year who are killed by accidents, estimates range from 44,000 to 400,000 on that. Whether it's that we spend more than $4 trillion a year on healthcare in the US, but at minimum 1 in 5 of our fellow citizens can't afford their care. Whether it's that healthcare is the largest employer of any segment in the United States, and yet we graduate 3 full classes of medical schools to fill the chairs of physicians who committed suicide in the last year. The statistics bear out the lived experience. Even accounting for the fact that healthcare today is the best the world has ever seen, there's a lot of opportunity for improvement. And that these things derive from the fact that the system is complex, that makes it hard, and that it requires innovation to make things better, which is why you all are here. So we've been asking the question over the last 5, 6, 7 years of whether technology like AI and ML can help with this complexity. But I wanted to start off with what I suspect are shared beliefs. And so I often get asked this question of, will healthcare be different because of artificial intelligence? And if a conference organizer wants to be a little bit edgy, they ask, will healthcare be disrupted because of artificial intelligence? And I love this question because I can just say, yes, thank you, you've been a great crowd. But the real question is when and how. So there's this great quote by Bill Gates that we always overestimate the amount of change that will occur in the next 2 years, and we underestimate the change that will occur in the next 10. And I think that's about right. People say, oh, it'd be tremendous change in the next 18 months. Yeah, maybe. Next 10 years, pretty confident that that's about right. My guess is we're probably 3 years into this 10-year cycle at this point. We're starting to see some change. But it requires patience to see change for patients. And so in that context, what do I think clinicians and healthcare leaders need to know about machine learning and AI in healthcare? If you only walk away with one thing that I say, it's this: it's math, not magic. And what do I mean by that? I mean, it is easy to chase the shiny metal object. It's hard to think of anything except for maybe blockchain that is more hyped right now. And so if you only remembered one thing that I was going to say, it's bring your native skepticism to the table when someone comes and says, oh, ML can figure out the best treatment for every patient, never having to randomize them again. Well, like, show me the math for that. I often get asked why, so our group for a large technology company is fairly unusual. We have, actually, I just got the updated number today. So we have about 150 peer-reviewed publications in health. And I often get asked why we publish in journals like JAMA and Nature. And the one thing I can tell you for sure is that it is not because journal editors move at the speed to which Google is accustomed. Rather, it's because of two things. One, we think the math is hard. It's important to get the math right. And we think peer review helps with that. And the second is that we want to show our work. We want to show where we started. Can this, look at lung cancer screening, CAT scans, and then be able to show the work along the way, because it's part of how we build trust in AI, and also how we tell if it actually works or is just another piece of technology that's fancy. So if you only remember one thing I say, it's math, not magic. Bring your native skepticism to the table in the same way that you do when you see a new drug come out. But it is a new technology fundamental. What do I mean by that? I mean, like, connectivity is a new technology fundamental. When your computer is always connected or your cell phone is always connected, you can do different things. AI is a new technology fundamental. I'm going to give two examples of that. Both are literally on my kitchen table. So I moved to California as part of taking this job. Most of living in California has been great, but it turns out when you go west of the Rockies, the bugs change. And so I was eating lunch, and this thing crawled up next to me. And I was like, oh, am I already dead and don't know it? Is it an alien? Like, what is this thing? And so I took a picture of it. And the sharp-eyed among you will recognize that this is Google Photos, but it's like running on an iPhone 6 or something like that. And I just, if the video works, fingers crossed, hit the button, and it says, oh, that's a Western tussock moth. Click here for more information. It's pretty amazing that that works. Here's a second example on my kitchen table. So Tom knows this, I was an Asian studies major as an undergrad, focused on China, and I was never very good at Chinese. And so I have all of these not very sophisticated books laying around. And we're just gonna watch this video, watch it twice. Okay, and so this is Google Translate, again, running, my Android colleagues would be mad at me, running on some old iPhone that I have, and actually running locally in airplane mode. And now let's watch it again. So it's gonna predict which pixels are language. It's gonna use a sequence-to-sequence model to translate those. It's gonna predict which color, which font, and which pixels it needs to interpolate to show you that car is chicha and train is huacha. If you'd asked me 10 years ago, would we have this? I would say, yeah, for sure, but I will definitely be retired by the time we have it. And now it's on the phone and running locally. So those are things that are feasible now that were infeasible before. And so the real question is, can ML make new things feasible in healthcare too? And we're starting to see some lights on the runway that the answer to that is yes. So, machine learning gets bandied about a lot, but it has this one key insight that I think is really important, and it's this. It's that it is now easier to program computers to learn than it is to hard code them to be smart. I'll say that again. It is now easier to program computers to learn than it is to hard code them to be smart. I'll give an example for a spam detector. So the way you used to do this is you would take some data and a program and run it, and it would give you results. And that looks like, if email contains this funny misspelling of Viagra, then mark is spam. If email contains something else, 100,000 million if then else. The approach with machine learning is take some emails, have some people classify them, spam, not spam, spam, not spam, learn what that pattern looks like, see how well it works, and then rinse, lather, repeat. And it's not that theoretically this is better, it's just that empirically it works a lot better, certainly in spam detection, but also in a number of other areas. So this is the part that, I don't know how well this part is gonna work, but when I moved to Google, and I was just an individual contributor for the first 6 months, I had the chance to be in the group that develops new kinds of machine learning. And it was really helpful to be able to, when you're like, oh, I don't really understand Word2Vec, to like turn next to you and it's like a named author from this like famous ML paper. And one of the things is that the fundamentals of machine learning are pretty simple. And so I'm going to make an attempt to give you an intuition for this. And so every ML thing has some picture that looks like this, which is fundamentally unhelpful in understanding what's going on. So I'm going to zoom in on this one little circle, which is a neuron, of like, how does it make a decision? And we're going to start with something that looks familiar. So here's some data. On the x-axis, we have age, and on the y-axis, we have some numerical outcome. Systolic blood pressure, LDL, whatever you want there. So you're asked here, given somebody's age, what is their most likely numerical outcome in a new set? And what do you want to do when you see those data? Like in your heart, you desperately want to draw, who said draw a line? You want to draw a line. Like I look at that and I'm like, draw a line. Yeah, you want to draw a line because your eye is a pretty good statistician, it turns out. So great. Anybody remember the formula for a line? Y equals mx plus b, Rice grad coming through over here. So y equals mx plus b, that means that a line is defined by only two things, by slope and by intercept of the y-axis. Line is defined by only two things, by slope and by intercept. Awesome. Okay, so now we're going to draw a line. That is a terrible line. It's really bad, right? The interesting question is, why is it terrible? And it's terrible because it misses the data a lot. And so we could draw a lot of lines. In fact, we could draw an infinite number of lines. And how do you know which one is best? Well, your eye is really good at doing this. So here, that line is the best. And the reason it's the best is because it misses the data the least. It's closest to the data. And so there's a formula for that. The important part is there's a formula for it. And that formula, you can draw these little lines and you can square them and all these things. But the key part is there's a formula. And once you have a formula, the computer can optimize for it. And so here's what it does, is it draws a line and then it just varies the slope and the intercept until it misses the data the least using that formula. So we're going to draw a line. Okay, that's pretty bad. A little better, pretty good. Oh, getting worse. Let me go back. That's the place where it's least. And so there's a whole bunch of very technical optimization about how do you vary the slope and intercept? How do you do it in 356 dimensional space? But it all basically does that, is it looks for where you miss the data the least, and then it just picks the one. And the important part is that computers have gotten fast enough, and there have been some optimizations in the architecture of the actual chips that let you do that very fast at scales you couldn't do before. And so the key point is that nearly all machine learning algorithms do some version of this. And everyone here will recognize that that was just a linear regression, right? The easiest form of machine learning. But if you ever look at a perceptron or a neuron, they're not much smarter than just a linear regression inside of the individual thing. You just network them. And so the same holds true for more complicated algorithms. So I showed you linear regression, but this could have been a support vector machine or a convolutional neural network in LST, and they all do some version of varying the slope and the intercept, which get the name of weights. There's some translation table, I believe in my heart, between epidemiology and machine learning. and they try to minimize this error, those little red lines. That's it. So let me give some examples of the way we use machine learning. And we have 3 areas that we think we can lean in and be helpful. And we have some lights on the runway and some evidence that this is the case. So the first is that we want to help people in their daily lives, because most of their life is spent outside of a healthcare facility. And so we want to help them in their daily lives, which we think of as consumer health. We want to help caregivers, and here we mean doctors, nurses, hospitals, everyone in between. And we know that where we live, work, learn, and play determines the majority of our health outcomes, as much as the ICU docs among us would like it to be otherwise. And so we think a lot about understanding and helping with community context. And so I'll show you concrete examples in each of those buckets, but that's the overall architecture I'll show you. And so inside of consumers, I often get asked people in health. And there are a lot of reasons that we're in health, but a fundamental one is that every day, hundreds of answer those questions. I'm going to tell you my favorite statistic I've learned since I came to Google, which is that of the trillions of searches that get typed in every year, 15% will be brand new, never typed in the history of humankind before. And I had trouble believing that. But when I start taking, if we just take English and we take, 52 capitals, lowercase, and then add 10 and 62 for one character, and then we have 2. Now we squared it. Now somebody types 30. I don't know what 62 to the 30th is, but it's a large space. And so language is a very high dimensional construct. So we, dealing with this and still giving good answers that are helpful to people is a very hard problem. And we've made a number of fundamental machine learning advances in how to do that. So moving from older ways of doing it into these things called transformer models, into bidirectional encoding transformers or BERT, into newer language models. A lot of that has been driven and then open sourced out of our group because we needed to give good answers to those questions because 15% of them are brand new every day, continue to be. We do a lot of work in sensors. I did not quite update this. So this is continuous atrial fibrillation detection based on a PPG signal done in one of the largest consumer health studies, the Fitbit heart study with 456,000 enrollees, was just published about 10 days ago. I forgot to update the link. So the study design, an HA presentation are there, but it came out in circulation, I think, about 10 days ago. And so this is what we're trying to give people using machine learning and other technologies the ability to understand and act on their own health in ways that weren't possible. This is one of my favorite things that we've done. So when some people are asking, can you check heart rate and respiratory rate just based on the camera that push the results? And on Pixel, we know a lot about the Pixels. Here's what it looks like counting respiratory rate. Docs, oh, I see an IC doc. So this thing is looking at very small little movement. For all the world, that looks like a volume time tracing on a mechanical ventilator. I'm gonna hold my breath. See little cardiac oscillations in that? So that's just, again, running on the phone, you can go get it. And one of the things that I've enjoyed is we're able to do clinical and bring them to people at scale. So this was launched on the Pixel. A year later was launched on more than 100 Android phones for folks. Those are examples, humor side, ranging from search to AFib detection to stuff you can do just with the camera, of the ways that we're using machine learning and AI. Again, new capabilities that didn't exist 10 years ago. And then for clinicians, I'm going to talk about computer vision for a second. So there is this relatively common competition and task that computer vision algorithms get asked to do. And in 2011, so this is or a leopard or a cheetah or a dog, it messed up 26% of the time, 1 in 4. Not really good enough to do anything with. Humans mess up this task about 1 in 20 times. And since 2016, computers, because of technical advances and advances in the amount of computation that can be applied, have performed better than classifiers on this particular task. And it just keeps getting better. And so the reason this is important, if you think from an evolutionary biology standpoint, the moment that animals began to be able to see and perceive the environment around them was a very important moment in evolutionary biology. And that's what happened in the past decade in computers. Computers can now see the world around them. And so I'm just going to give you examples of work that we've done. We've done work in radiotherapy planning, which is any radiation oncologist here, very time-intensive task of you want to plan a radiotherapy field for head and neck cancer. It takes hours of circling, this is the cancer, that's the carotid, don't buzz that. It turns out that you're able to do that with computer vision in ways that are equivalent to US board certified radiotherapists. We've done a ton of work in pathology, and our overall architecture of research in this area is we do work with offline images. So we'll have pathologists go and circle the cancer and all of these things to show that the algorithm works. Then we usually do human-computer interaction studies because it turns out that a pathologist plus an algorithm performs differently than a pathologist or an algorithm. And they have different strengths and different weaknesses. And so we learn a lot about that. And then in some areas, we move into randomized controlled trials as you would with any medical device. And so these are examples of some of the closer to basic science work, some of the pathologist algorithm interaction papers. And this is an example of an augmented reality microscope where you put the physical slide on the microscope, move it around. I was always very bad at path. And it just circles the cancer they're running live on the machine. Our oldest work is in eye diseases. So diabetic retinopathy is the leading cause of preventable blindness in the world. Screening prevents blindness because we now have effective treatments for early stage diabetic retinopathy. But in many areas of the US and in many countries in the world, people don't have access to screening for diabetic retinopathy. It's how many physicians in the room? Who feels comfortable looking in the back of the eye and grading diabetic retinopathy? Yeah, it's I'm definitely not able to do that. So starting in about 2014, the team took a bunch of pictures of retinas, had a bunch of ophthalmologists rate them, mild, moderate, severe, proliferative, none, skipped none. And then showed that a convolutional neural network could perform equivalently to US board certified ophthalmologists. Then subsequently was able to show that if you took a retinal subspecialist and trained on their gradings, that the algorithm could outperform average US board certified ophthalmologists. We have a collaboration with a couple of companies where that device is in the field now and has screened more than 100,000 people for diabetic retinopathy. But this is our longest field. This is just a list of the publications in the eye disease space. And breast cancer is one of the areas where we see a lot of potential for AI. So we've shown that the algorithm in images can perform equivalently to radiologists. But one of the really important things is you're beginning to think about taking an algorithm to helping actual people is being very specific about the problem you're trying to solve. And so the problem that we're trying to solve now is any of us who took care of adult patients for any length of time have had a woman who's come in, had a screening mammogram, goes home and waits days or weeks to get a result, only to get called back in for diagnostic films. And then there are really only two outcomes. Either there has been days to weeks of suffering while waiting and not knowing, or there's a delay in diagnosis of something that needs a biopsy. And so with Northwestern, we now have a randomized control trial in the field asking, can you, at the time the woman gets the screening mammogram, can the AI read the screening mammogram? And if it's worried, ping the radiologist and say, hey, do you want to get diagnostic films while the woman is still in the room? Asking, can we shorten the time to final diagnosis there? And then with the NHS, we are about to have a trial in the field. You may know that the screening regime in the UK is different. That for release of a mammogram, it requires 2 mammographers to read the mammogram and to have concordant results. And so we're asking the question of, can you replace one of those with AI to shorten the overall cycle time? And so again, adapted to the specifics of the health system, but a good example of the use of AI to begin to take some of the waiting out while supporting physicians in decision-making, certainly not trying to take decision-making away. So those are examples for caregivers. And then in the community context, we've done quite a lot of work. I'll give one example. So we have a team, you may know that river-based flooding is life-threatening and kills thousands and thousands and thousands of people every year, particularly in India and Bangladesh. We had a team that figured out that you can use ML approaches to forecast the floodplain and give people warning ahead of time before they have to leave. Showed that algorithm worked better than prior flood prediction efforts. And then they were able to implement this on Android, and last year served alerted users 150 million times of floods that were coming toward where they were at the time. So it's one example of how we think about health as an integrated continuum between climate and health in the individual doctor-patient interaction. COVID was a turning point for us as well. So we did a lot of work to help people get through the pandemic, whether that was figuring out where to get a vaccine. It's a complicated little problem. Whether it was showing people COVID statistics, which turned out to be one of the things that people were the most interested in, of what's going on with COVID in my local community. We worked with Apple to have exposure notification that ran across iOS and Android. I just learned an hour ago that the Missouri server for that is done here, is run out of WashU for it. The US did not have a huge uptake of this, but other countries did. Team from Oxford estimated that the deployment of this prevented in sort of phase 2 of the pandemic between 252 and 476,000 cases. And then we worked on Android and again across to iOS to let people prove their vaccination. We also tried to help public health agencies and researchers. And so we did things like make aggregated anonymized search data at a daily and roughly county basis available. People had questions of what are people actually searching for. This is just a time series of fever, I think, and if you track this against COVID waves, turns out to show up pretty well. We were able to cross the tools in maps that tell you, oh, it's going to take you 36 minutes to get somewhere. With vaccination sites to help with, in a partnership with Boston Children's, to help with vaccine planning. Because it turns out 5 miles in some places is 5 minutes of time. And in other places, 5 miles is 4 hours of time to get from one place to another. As the vaccine rolled out, there was a lot of interest from public health of whether people were searching for, how do I get a vaccine? Or will the vaccine give me inject a microchip in me? And so we were able to aggregate and anonymize these and make them available to anyone who wanted to use them. And then we worked with the WHO and served 2 billion, slightly over 2 billion COVID-related public service announcements about COVID across the world. But these areas were our attempt to make data available for researchers and for public health. And we asked the question of, is it helpful? These are 2 Google Scholar searches for Google Trends and Google Community Mobility Reports. We know that more than 1,000 peer-reviewed publications were published using the data sets that we made available. And so it was a proof of concept for whether we can make data available that's helpful to the community. So those are the 3 areas where we've done work: consumers, caregivers, and community context. And we talked about 4 things. If you only remember one thing, math, not magic. Most important insight of machine learning is that it's now easier to program computers to learn than it is to hard code them to be smart. Try to give an intuition of how machine learning actually learns. And then we give some concrete examples of ML in consumer, caregiver, and community context. Thanks.
Questions?
Thanks, Michael. Great job.
Yeah.
So what's the role of the physician moving forward? And where's the sort of artistry still remain? Or will it still remain? Seems like this capability will just continue to expand and fill spaces that historically perhaps have been filled by our brains.
Yeah, I'm less worried about that. So the two, you've known me long enough to know I reason by analogy, right? So I'll tell you the analogy that I think this is the right analogy. So when I was in high school, my mom was an accountant. When I was in high school, I worked a couple of summers for her doing bookkeeping, and it was long enough ago that you had like physical sheets of paper, a ledger, and you had a 10-key adding machine. And I would always like lose 25 cents, and she had like this superpower to go find it. You would add it and like write the number down and reconcile and do all these things. And then like somebody invented Lotus 1-2-3 and Excel, and that kind of bookkeeping went away. But accountants didn't go away. Even bookkeepers didn't go away. But the work changed. And so I think that's the right analogy for where we are now. I think the healthcare analogy is, there was a period of time when only physicians were allowed to take blood pressure. And then nurses were allowed to take blood pressure. And then you could go to CVS and get your blood pressure taken, or Walgreens or wherever, Rite Aid. And now you can do it at your house. And so I think that many of the things that I think we're likely to see the kind of work change, and that I think that we're likely to see machine learning and artificial intelligence be belt and suspenders and decision support and that over time, we'll see some areas where when you do the randomized control trial, you'll learn what's better in that regard and what's not. In the adult, Julie and I are both intensivists. In the adult context, in the 2000s, there was this randomized trial of like, let respiratory therapists decide when to extubate people. And it just turns out to empirically be better. I think there'll be a couple of those of, there'll be some medication dosing thing or something like that. But most of it, I think our expectation is augmentation rather than replacement. That answer your question?
Thank you. That was a very good talk. When I think about machine learning AI, I think about it in the context of machine processing information that's deliverable and actionable by an end user like a clinician. And technology in healthcare currently lags behind a lot of other industries. And other industries are dealing with issues like cybersecurity and attacks like that. Does Google, or your take on this, as we become more reliant on technology to make healthcare decisions or provide healthcare information for those clinicians to make decisions, what is the role in developing strategies to prevent these sorts of attacks on things like Internet of Things devices?
Yeah. Well, I don't think it's a theoretical risk. I think it's, the number of cybersecurity incidents in healthcare provider organizations has only gone up, as I'm sure you know, and there's news today about that in some places. So I think there are two different parts of your question. So one is, by definition, anytime you change something in a complex adaptive system, your prediction of what that change will do as an outcome is suspect, right? That you need to treat, measure, treat, measure, treat, measure. So that's one. And changing to be more reliant on thing A versus thing B is a change, for sure. But you could say that about electricity in a hospital. Thing number two is, what is the importance of security in this time, and what is the way to defend our patients? Because the creativity of human beings in pursuit of money is very high, and they're willing to put people at risk to do that. It's really important, and historically, having a server that ran under your desk in Division X and Department Y was okay. But I think empirically we're finding out that it's not that now. And so that is one of the reasons that we're seeing, that's one of the reasons that people talk about for reasons to move to cloud instead of an on-prem based approach to this, is because large cloud providers employ a ton of security engineers that health systems can't employ the same number of them. And so I do think that that hardening up on security is really important in an era when the computer systems are already critical to the care of patients. That answer your question?
One question I have is, I agree with you that information more and more is becoming, I think you said earlier, a determinant of health.
Yeah.
And so that stands to reason that information access is now an enabler of health. And if you don't have access to it, it's a negative enabler of health. So when you think about what I'll just say, the data and device infrastructure needed for people to do what you just showed they do in terms of searching for health or accessing the tools, how does Google think about that?
Yeah, I'm going to extend what you said, that the information needs to be available and it needs to be accessible, and that there are ways to quantify the accessibility of information through health literacy tools. So we do believe that information is a determinant of health. And we believe that we have a particular obligation to help people find helpful information about their health. What we're learning is that some people want text-based things, and other people, really large numbers of people, want to watch a video of somebody telling them what to do. So we've been investing. I'm gonna take YouTube for a second. So YouTube is a video sharing platform. About a little over 2 billion people, about a third of the world's population goes to YouTube every month. And a substantial number of people ask questions about their health on there. So I'll tell you two ways that we've been approaching this specific problem. But it's in the context that we know from good studies that video can make complex concepts more accessible to patients and to people when it is accurate information, and that it's a risk vector when there is engaging information that is wrong. So in COVID, we did an intervention to try to get more people to see good information, where it's probably, I haven't actually looked today, but it's probably still live, that if you search for COVID, at the top of there'll be this little box, and it'll say, for more information, go to here. And it'll take people in this room to the CDC. If you're in London, it would take you to the WHO. If you're in Ghana, I think Ghana would go to the, sorry, if you're in, it would take you to the NHS if you're in London. If you're in Ghana, I think it would take you to the WHO. That little thing has been viewed more than 400 billion times. 7 billion people on the planet, that thing's been viewed more than 400 billion times. And so that was a public health messaging campaign to make sure that people had the most accurate information and easy access to it at a time when, particularly early in the pandemic, when information was fluttering around a lot. But we're in a different phase of the pandemic, and COVID was unprecedented in our lifetimes, and yet more people died of high blood pressure last year than died of COVID. So we've been working on YouTube on what are the underlying principles by which you would identify credible health information? And we don't want to be doing that. And so we worked with the National Academy of Medicine, who had a landmark expert panel paper about what are the principles for identifying credible health information on social media, subsequently examined and validated by the Academy of Medical Colleges and the World Health Organization. And then we operationalize those principles in YouTube. And so today, if you go and search for diabetes or whatever, there'll be a thing at the top that for the top health intents that shows from health sources, where health sources are things like the NIH or the CDC or hospitals accredited by Medicare. And we've been able to scale that to the US, UK, India, Japan, Brazil, and Indonesia so far. And we'll keep investing in that of external principles of how to identify the best information that we then try to operationalize. I feel like there's a long answer to a very straightforward question, but did I get it?
It's great. I also think, and I don't know if this is in Google's scope, but everything you said is predicated on somebody being able to access YouTube. And so if I don't have a phone, if I don't have a data plan, if I'm in a remote area of Bangladesh, and I'm not saying that Google has to solve this problem, but I'm curious if you guys have thought about moving in that arena as well.
Yeah, so there are two different ways to be helpful here. So one is make the information that we have more easily consumable and accessible by the roughly half the world's population who eventually can have access to it. The second is what can we do to promote fair and equitable access to things like broadband or 5G? We have a number of efforts around that, both in the US and externally. But in some ways, so that's a general thing that Google works on and has worked on for a number of years. On the health side, when the ball is thrown to us, we want to be able to catch it and do a good job. And so that's my team and other teams like Garth Graham's. That's the place where we're investing the most. One of the really interesting things about this is, something that like you all could go do tomorrow. So we've taken really important real estate on YouTube and made it available for hospitals, health systems, areas like that. Turns out that sometimes the videos are really boring. Somebody standing at a lectern for 40 minutes talking. And so the ability to make videos that your patients want to watch to get the information that they need is something that I think as a profession and as a health system and as people who are concerned about people getting the best information and wanting it, I do think that that's an area that we are working to try to help health systems and others do better on.
Analogy, it's a more palatable pill to take.
Yeah, sometimes videos are not good.
You had mentioned in the beginning this issue that hospitals confront with not growing too fast, maybe growing too slow, and then having a census that they can't navigate. It's interesting to me because when you actually show up in places like ICUs, a lot of these places are still running on paper. by the amazing charge nurse that can navigate where everybody is going and when they're going. And it seems like that's something that would be quite navigable by machine learning and sort of the ability to operationalize that. Is that something that you guys have any insight on or potential to work on?
Yeah, so it's part of a general set of problems of constraint satisfaction problems and of scheduling problems. So we have a lot of like two examples of like how do we route data center traffic is a good example of scheduling problems. Or anybody ever use Street View on maps? Turns out like making sure those cars go to the right place is a hard math problem to do. So there are both kind of ML things and then kind of core, mathematical optimization approaches. There are a bunch of companies that are in the space of offering scheduling-based solutions. For all I know, you all have multiple contracts with multiple of them. But it does seem like a thing that's likely to be tractable over time once you understand what the rules are. And the lived experience, having been responsible for a number of ICUs over time, is that it's always that Bob or Mary has some set of rules in their head that are critical, and if they're ever off for a day, like everything falls apart. But it's hard to figure out what those rules are that they're using. We've got 3 patients on ECMO on this floor, and so even though this other ICU doesn't have any ECMO patients, we're going to put an ECMO-capable nurse in that ICU so she can or he can float over. If there's a bunch of other knowledge there, but the core problem of getting from a default thing that's terrible to pretty good, that seems tractable to me.
So I have a question about what you guys do with this data. So as time goes on, you'll have hundreds of thousands of mammograms, hundreds of thousands of pictures of people's eyes. Are there bigger questions that Google is trying to answer? And how are you going to use this data to answer that?
Yeah, there are 2 questions in there. One about trust and one about can you find new and interesting things in these data. And so there are 2 parts of trust in health. So one is when you share your data with Google, do we private? Do we secure because if secure it's not private? Do we make it so that you have control over it and know what to expect and don't do surprising things? So those are critically important. We work a ton on them. Things like on the consumer side, you can set your Google account to like auto delete after 3 months, like all those things. So that's really important. The second kind of trust is one that we only earn over a decade or more, which is do the things that we make in the healthcare space, do they help actual patient outcomes? And do they help doctors and nurses and others do their job better in a way that we can prove? That's part of why we publish, because we want to show the work as we go along. The specifics of how we handle data. So we have a product, for example, that is helps clinicians find information in EHRs. Those are delivered under a business associates agreement, fully HIPAA compliant stack, follow all the rules for that. Sometimes we use fully de-identified data. So chest x-rays that don't have any identifying information on them, that are most of which are publicly available. And sometimes when we run a clinical trial, we have a specific contract with whoever's running the clinical trial for the access to de-identified data. This one actually runs sort of locally, and every patient is consented just like they would be for a regular trial for that. Did I answer that question? Yeah. Okay, and let me tell you that sometimes you do find these really interesting things. And so I'll tell you one from the eye disease stuff. It's mind-blowing to me. So take a picture of a retina And someone wanted to do can we predict the 5-year risk of major adverse cardiac events, death, heart attack, whatever, from a picture? And it turns out, yeah, pretty well, you can do it. So we had that data set. When you take when we take interns or people who are joining Google, programming stuff at Google is complex because there's a lot of infrastructure. And so they typically will give them a task that is easy to do and one that's impossible to do. And so they had this intern and they gave her the task of predict the patient's self-reported sex, male or female, from a retinal photograph, which is obviously impossible to do. And they're like, this is going to be really hard. So she goes away and works on it, comes back, says, yeah, it's really hard. I only get an area under the curve of 0.76. The senior engineer is like, ha, 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 you have a bug in your code, go figure it out again. Comes back, she's like, yeah, I did have a bug in my code. Now it's 0.84. Senior engineer is like, oh, let's go look and find all your bugs. No bugs in the code. And so it turns out when they optimize this, that from a picture of the retina, you can predict self-reported sex with an area under the curve of 0.97. And again, physicians in the room, that's insane, right? You talk to ophthalmologists about that and their head explodes. They're like, it's impossible. And it seems like, okay, maybe we're leaking metadata. And so they made it so it runs on a device with no Wi-Fi and go around and take pictures. It always works, right? And then they do ablation experiments about, is it the retinal disc or the all these things. But those kinds of things, that's a fundamental biological discovery that was unknown before and should prompt a lot of basic science about what's going on there. And so I think that as computational power becomes more widely available and things that used to take us 100 engineers in 3 years to do at Google, now you can run with a account with any cloud provider because the computation has gotten so fast. I think we're going to see a bunch of discoveries of biomarkers that we had no idea about before. And that's an example of one.
Our next question comes from a participant online, actually.
Great.
And the question and comment is that they're excited about all Google's efforts in health, but that they appear to be on the periphery for the example that you provided around YouTube. The question is, what do you believe are the largest barriers to Google and other large tech companies playing a larger role in healthcare delivery? For example, scaling Care Studio.
Yeah, so we think a lot about health, of which healthcare is a component for that. And we spent some time, particularly during the pandemic, when during the pandemic, coronavirus became the largest information need on the planet for our users. And so it is very true that those things are on the periphery of healthcare delivery. It is also true that those things are central to people's lives as they live their lives. And so we will keep focused on how do we think about information as a determinant of health for people as they live their daily lives. The second part is, how do we take these innovations and scale them so that 1 million physicians, millions of nurses, tens of millions of patients can benefit from them? And we're trying to we think this work is really hard, and we're trying to be pretty methodical in how we spread it because we want to know that it works before we spread it. I think any of us who have been in the healthcare innovation space for a while have seen innovations that spread across the healthcare delivery system and were wrong. And so I'll give an example from the adult ICU of type glycemic control for all patients. Spread everywhere based on one crummy randomized controlled trial, became part of pavement measures. And there was an editorial published in the Blue Journal, one of the American Journal of Respiratory and Critical Care Medicine, that estimated around 26,000 deaths a year caused by wide implementation of that. So I think that's a wild overestimate, but I am sure that the number is larger than 0. And so we want to be careful about understanding how these things actually work, and then helping them to spread. I mean, Google is a company about serving billions of people. But I hope that answers that question.
I have a question about in most of the examples that we used to see here, or we see in healthcare, we see examples of machine learning. And basically, I'm going back to the examples that has been discussed about the ICU or tele-ICU, or situations where you really need to take an action immediately, or there are real-time data that not only requires knowledge in some extent, or requires, as you said, just something else. What maybe this difference between AI and machine learning, what it may include approximate reasoning, or reasoning in some ways, or operational research in some extent, what is in another level, no? Of another layer probably. So the question is, how does Google envision this jump from the inductive learning, what implies data-driven stuff, from a possible next step in terms of reasoning logics of beliefs, or whatever would be the next level, or if you have the next level?
Yeah. I'm gonna have two answers to that. One of them is, there's some really interesting writing coming out of the Stanford group now that talks about thinking about machine learning algorithms as part of a total value of information across the workflow. And that there are plenty of times when a predictive model, perfect predictive model versus random predictive model, doesn't change patient outcomes because you have downstream blockers in capability. And I do anticipate that we're likely to see more things that are focused on ML that look at the prediction or classification as part of a workflow challenge in the way that you talked about sort of operations management research. The second piece is, everything that I talked about is specific artificial intelligence versus general artificial intelligence. There's a ton of research going on about general AI that can do reasoning. And you never know when some new discovery is going to happen, but certainly we don't see things like that in the next few years. The person who hired me at Google, a guy named Greg Corrado, invented some of the core parts of machine learning. Things like, any ML people in here? Like Word2Vec is this so Greg is a named author on Word2Vec. Greg describes the current state of ML in healthcare like this. If you ever worked on a car, you need a wrench, like a crescent wrench. It's really important. But then you get a vice grip, which can keep holding it, and it's much better, and it helps you a lot. But it's not diagnosing and figuring out what is going wrong with your car and then fixing it autonomously. He's like, a vice grip is an amazing thing. Greg works on a lot of cars. So I think that's a ways off. I think that some of the things that we think of as data-driven empirical learning, they can have this slight appearance of magic to them. So the things I showed about translation, or this is a Western tussock moth, or some of the newer stuff that we have demonstrated around machine learning models optimized for dialogue. Those begin to look more like they're reasoning, but they're just learning from data. Somebody probably will get general AI that can reason at some point, but it seems like it's a ways off to me. Yeah.
One quick thing, I was fascinated, as you mentioned about being able to look at the retina and determine the patient's self-described sex.
Yeah.
A key aspect of machine learning has been described to me is that it's a bit of a black box. You identify these associations, but you don't know why. And have you been able to drill into that with
Yeah.
your capabilities so that you can then go back and figure out, well, what was it about the retina that was able to tell the computer to figure out what was the sex versus well, this is kind of fascinating, but we don't know the why of it. And this is, I know a lot of people worried, if you will, about this black box machine
Yeah, for
learning.
sure. Is there a way to show the picture again? Did it kick it? I am sharing my screen. They could project. I have to go back and do a like chalk talk. Oh, here. Okay, I may have to draw again. Yeah, so our group, so Google has a large research group, and in that is a group that develops new kinds of machine learning. And one of the things that they've been working on since I joined has been explainable AI. And so I think that there's a question of, will explainable AI be helpful? So if you went and walked around here and grabbed like 100 random physicians and said, "Do you see a potassium today?" Great. How did they get that number? People would be like, I don't know, right? How did they get the white blood cell count? I don't know the answer to that. So I think we should study whether explainability is important. But we have been investing, and I'll give an example from the retina where, so the way that we did the diabetic retinopathy study, so you have a 5 outcome classification: none, mild, moderate, severe, proliferative. The ophthalmologist did not go and circle what they thought was important. They just gave this classification. Now 100,000 of them, a little bit more. Now you train an algorithm on that, and it turns out to work really well. But then you can go back, and inside of the image of the retina, you can knock out a pixel. And then you ask, does that pixel change the accuracy of the prediction? Now knock out the next one. Now knock out the next one. And so then what you actually get is highlighting of the important pixels in that image through an attention-based mechanism. And there are different ways to do attention, but that way of knocking out a pixel tells you that, oh, it cares about it cares about looking along the blood vessels, or it cares about looking at the optic disc, because when it takes them away, it doesn't work. For the sex-based thing, we did a bunch of experiments on that. Knock out the optic disc, knock out this, knock out the other, and it's just a diffuse problem. So we still don't know what it's actually looking at for that. But for other things, you look at it. The example I was going to show, I have a real example, that's all right, which I'll show you after. And it highlights these little microaneurysms and microhemorrhages, and it ignores a dust speck on the camera, which looks to like a non-trained eye, like it should be highlighting that. And it ignores some other things on the picture pretty well. You can also do that in notes, physician notes. So you can say, oh, we want to predict readmission, and we're going to have, creatinine, pressure, all the things, but you can have it pay attention. It will show you what areas matter to the prediction in a way that when you look at it, it makes sense. And we've published a few things on that. Sorry for the long explanation there.
Well, I'll have one more sort of follow on to that. One thing that I've wondered about is the data inputs in more traditional modeling.
Yeah.
It's very important to separate variables that are relatively fixed, like your eye color or your age or whatever, and things that can be biased by marking an intention to treat. So for example, in sepsis, a classic one is, lactate is a wonderful predictor of impending sepsis. But that's because a care team member has already kind of wondered if you have sepsis in order to lactate. So I didn't know if there was a way with some of the ML technologies or just ways that you guys have approached this to start to somehow say what seems to be inherent in the phenomena we're looking at and what just may be a little bit of a byproduct of the system already anticipating what we think we're looking for.
So there are some model structures that are, there are two different problems here. So one is you have things that are fixed, and the other is you have things that are dynamic. And there are a bunch of model structures that are good at dealing with sort of disentangling those. But the other problem that you're talking about, if I were to put on my epidemiologist hat, would be missing data that are missing from a non-random mechanism. And non-MCAR missing data is a lethal statistical problem. I'm unaware of ways to deal with that. And it's in particular lethal because once it's in a data set, once you have a data set, I think it's handed, you can't figure it out later. So this is one of the things that the causal modeling community, I think, are really working hard on. But it's a thing that when I see papers that say, oh, we looked at, we used reinforcement learning to figure out all of these optimal treatment pathways, it makes me very nervous about that. So we have a bunch of groups that do research on that. Many people have groups that do research on that, but I'm not sure whether it's just an extraordinarily difficult problem or whether it's a theoretically impossible problem to solve. The other place that this general thing crops up is, we call it training serving skew. So the probability of being in a training set is conditional on a whole bunch of things that end you up in the training set. And that may change when you start actually deploying something in the real world in two ways. One is the population may change and you may miss that. The second is that as people respond to your prediction or algorithm, then your model will decalibrate based on treatment, which becomes another, that one is more tractable to deal with, but the missing at the beginning is really hard to deal with.
All right. Any other questions in the room or online? All right. Well, I very much appreciate the presentation and the
Thanks for having me.
thoughtfulness. And please join me in welcoming Michael. Thank you.